Welcome to Vector101. This is lecture 8, and today we're continuing our discussion from Monday on row reduction and linear systems of equations. But before we do that, we actually have some unfinished business. So here is the schedule, and we started talking about vectors in the first week, and we talked about the geometry of vectors in the second week. Then we talked about linear transformations, and so now linear transformations is actually eating a bit into this lecture today because we have to go back and talk about matrix multiplication. We have to code it. So we're going to do that for the first half of the lecture, and then we're going to get onto row reduction. And we probably won't finish our discussion of row reduction until next lecture, but I think that's okay because what we're talking about next has some overlap with row reduction. So yeah, but just keep this in your head. Hopefully you don't get confused with which concepts are being presented when. Okay, so our agenda today is we're going to start with matrix multiplication, and then we'll get on to row reduction, aka Gaussian elimination. And some reminders as always. It's very important that you do the exercises, and in fact, it will be extremely important more than ever this week because row reduction is hard. It's not hard. You just have to do it. Row reduction cannot be presented. It's something that you have to feel by doing. So I'm sure Aiden will probably post some exercises for row reduction by hand, and then my exercise to you will be to code it yourself. All right, and then as always, office hours are on Saturday at 1 p.m. Pacific time, where you can come and ask questions to Aiden and I. All right, so back to matrix multiplication, reaching back to last week, but that's okay. So what is matrix multiplication? Why do we do matrix multiplication? Well, it's because it describes the composition of linear transformations. So if we're given linear transformations T that eats from Rn and spits out into Rm, and S, which eats from Rm and spits out into Rk, then we can compose them. And what I mean is, so down here, if we take an X and we put it into T, and then we can put it into S. So this is composition. And note, the dimensions here are important because the thing that T spits out ends up in Rm, so S has to eat from Rm. Okay, and so on the right side here, I have, this is a new notation. We just really love inventing new notations here. This notation is just saying that this is the matrix representing the linear transformation T. Okay, and so because T is from Rn to Rm, this is an m by n matrix. And for S from Rm to Rk, this is a k by m matrix. All right, and so their composition is C eats from Rm, spits out into Rk, and what you do is you take X, you feed it into T, and then whatever T outputs, you feed into S. Okay. So this is composing linear transformations. And then we define matrix multiplication so that the matrix representing C is the product of the matrices representing S and T. So we don't define matrix multiplication by just saying this is how you do it. This is how you do it by hand. We define it so that it has this property. Sorry, I was reading comment in the chat. Okay, so this is why we do matrix multiplication, because it gives us the matrix for a composition. And I should say that this one is k by n. Okay. So now that we have our definition for matrix multiplication, how do we write down the actual process? Okay, so here we're going to derive matrix multiplication. And what we've learned last week is that anytime we want to write down a linear transformation, we watch where the standard basis vectors go, because these become the columns of our matrix. So here, this is going to be the ith column of C. So it's one of these guys. And well, what we learned last week is that what you do is you feed in the ith standard basis vector into C. And then, well, what did we say C was? Well, C was the composition of T and S. So just by definition of C, this is S of T of EI. Okay, and then this should look familiar because this is just, it's the same trick we just did. This is the ith column of T. So this becomes Ti, the ith column. Okay, so now we know that each of these columns in C is just S evaluated at one of the columns of T. So if you know how to do this, if you know, well, all right, so in the equivalent form is this, which is, it's the matrix S times the column T. And as long as you know how to do a matrix vector multiplication, you know how to do matrix multiplication. All right, so we're almost there. The last thing to do is to break down what is the matrix S times the column T. And well, we've seen this before. We know how to do matrix vector multiplication, so it's just this. So this gives another vector, and then, right. So we got the column, and now we can find an element in the column. So now we can pinpoint exactly one element, and the formula is it's this. So it's T1I. So it's the same from up here, and it's going to be S1J. Oops. All the way down to TIM SMJ. Okay. So that was a lot to take in. I mean, we accomplished our goal. We derived how you multiply matrices. And now you can just like dump that out of your brain. You can just garbage collect it because that's a lot to hold into your brain. And so we'll just like skip to the very end. Like what was the point of all this? Like this is what you should remember. Although I encourage you to go through this on your own. Again, I'm just saying that if you didn't fully understand this process on the first go, I understand. All right. So then the upshot to all of this is that if we want the ijth entry of C, well, maybe we'll just skip down here. What we're doing is we're doing an inner product of row I of the matrix S with column J of the matrix T. All right, so if we want the ijth entry of C, we're doing an inner product of row I of S with column J of T. I'm going to pause here for questions because I'm sure you have some. I'm just waiting for questions in the chat. I see people are typing. Okay, so your question is how do we derive a matrix from linear transformations? So right, like one of the big takeaways from last week was that to derive a matrix, so we can even just like omit this word here. Like to derive a matrix representing a linear transformation, we watch where the standard basis vectors go. So like if we wanted to write down T, well, I already have it written on the last slide. Right, so if we want to write down this matrix, the t-ith column is t of ei. Okay, question, does the name for this algorithm have a name? I guess kind of, we just call it like the naive algorithm, but there are faster algorithms, and I'll touch on that. That's right, Porb. Yeah, ei is the ith standard basis vector. Okay. Right. So like the upshot to all of this is that we're just doing dot products with rows and columns. Oops. Okay, to be clear, this is I and this is j. Okay. It looks like Aiden will help me out in the chat, so I'll continue on. Let's just do an example, and I think that will hopefully clear things up a little bit. So here we have a 2 by 3 matrix times a 3 by 2 matrix. And note that we're allowed to do this multiplication because these match, because the columns of the first matrix match with the rows of the second matrix. And this is like equivalent to what we said at the beginning, which is that like S has to eat from where T spits out. That's imagining like birds spitting. I'm not going to continue that comment. Anyway, right, so we're going to multiply this, and what we end up is, so these threes have to agree, and then what we end up with is a 2 by 2 matrix. So this here is, we're going to end up with a 2 by 2 matrix. All right, and so how do we compute A11? Well, we do the dot product of the first row of the first matrix with the first column of the second matrix. All right, and so this dot product is going to be 8 times 6 plus 4 times 5 plus 3 times 0, which works out to 52. All right, and now let's do A12. So this will be the dot product of the first row with the second column. This is 8 times 10 plus 4 times 9 plus 3 times 2, which is 122. All right. Now we'll do A21. So this is the dot product of the second row with the first column. 1 times 6 plus 7 times 5 plus 2 times 0, which is 45. All right, and then lastly, to compute A22, it's the dot product of the second row with the second column. All right, so this is 1 times 10 plus 7 times 9 plus 2 times 2, which gives us 77. So then in total, what we get is 52, 122, 45, and 77. All right, so hopefully it's like a little clearer now what we do. So we look at the ijth entry, and we do the inner product of row I with column j. And like that's what you should keep in your brain, because it's hard to keep in your brain how the derivation works. Like go through it once, but then just remember this fact. And so like I'll admit, every time I multiply a matrix, I forget this. And every time I have to think really hard about how to do it. So I don't blame you if you don't get it on the first go. All right, hopefully our short-term memory is long enough that we can now code it. All right, so what we're going to do, and I've changed up, usually we code in Roblox, but for today, I want to be able to like gesture at this image at the bottom. So we're going to just handwrite it for now. So we're going to multiply two matrices. We're going to take in matrix A, and we'll take in matrix B. All right, and well, first what we need is we need a new matrix to put the values into. All right, so we'll just create some C matrix, and this will be a matrix of zeros. And let's remember what the dimensions of this have to be. So if A is m by n and B is n by k, well, this is good. So the n's agree, so we're good there. And then C becomes m by k. So we're going to give it the rows of A and the columns of B. And I suppose what we really ought to do first is like verify that these match. So we really ought to put something in there like assert that the columns of A are equal to the rows of B. Sorry, forgot to put that in. Okay, so C is going to be our new matrix that we're going to populate. And what are we going to do first? Well, we want to populate each entry in C. So we're going to have to loop through every single entry. So we'll start with that. So first we'll loop through every row. So I is going to go through all of the rows, and then J will go through each column in the row. Right, and then we should close off our ends. I hope I counted this correctly. All right, so we're looping through each element, and then for the ijth element, we're going to do the inner product or the dot product of row I of S with column J of T. So we're going to need another for loop. So we're nesting quite deeply here. So now we're going to have another index. This is going to be K, and K is going to do this looping action. So K is going to go from 1 through what does K go over? The columns of A, which is equal to the rows of B. That's that N up here. All right, and then what we're going to do is the C I jth entry. We're going to add to it the product of A I K and B K J. Keeping track of these indices is kind of difficult, so let me go over this again. So I and J, this is the row and the column. All right, and then K keeps track of running through this row and column to do our dot product. And so, right, so we're going to multiply the first element in the ith row of S times this first element here, and then we're going to multiply the second element, and so on until we get down to the end. All right, I'll pause here again for questions. Oh, and I suppose at the very end we should return C. Aiden, is that a comment on the algorithm? Well, okay. All right. If we're feeling good about matrix multiplication, which I suspect the silence is that we don't feel good about matrix multiplication, but we're too confused to ask questions. But I'll keep going on, and please ask questions in the chat. Oh, this is not a good sign. Okay, well, all right. I'm glad you got it, JMK. Okay. This is a fair point, Borb. Well, let's definitely talk about it in office hours, and give you some time to think about it on your own before then. All right. So what we just coded is called this is the naive matrix algorithm. This is right. It's like the obvious one, but we can actually do better. I mean, for a long time it was thought that you couldn't, until this guy Strawson came around. It's possible that gets nuked by the Discord compression, but Strawson was the first one to come up with an algorithm that beat the naive algorithm, and since then there's been a lot of progress. So like what this curve is measuring is like vaguely, very vaguely, it's measuring like the speed of the algorithm. Which with a catch, which is that like these algorithms down here, they're wicked fast, but for like enormous matrices, like matrices so large that no human would ever like need these algorithms. So we call these galactic algorithms because like sure they are faster, but only when your input is just so galactic enormous. So like in practice, really what people use is just Strawson. And so Strawson becomes better than the naive algorithm around like when your matrix has like a few hundred rows and columns. So like that's, I mean, people work with matrices that are that size, so it's practical to have. And in fact, the RBX Math repository has an implementation of Strawson's algorithm from Aiden. That's right, JMK. And so what's interesting too is that this is like progress on just general matrix multiplication, but actually you can do better in certain cases. So if your matrix is sparse, which means there's just like a lot of zeros, then there are faster algorithms. And recently, who was it? Was it OpenAI? Some AI company found a faster algorithm using machine learning for 4x4 matrices where the elements are ones and zeros. So in certain cases, in special cases, you can come up with better algorithms. All right, but that was the naive algorithm. Oh yeah, Borb asks, why is Strawson written twice? And also, Coppersmith and Winograd are twice. And like Aiden, you should fact check me on this, but I'm pretty sure that the Strawson algorithm we use is the first one. Yeah, okay. I should also admit, I don't know at what point it becomes galactic. Yeah. These are definitely galactic, though. Oh, and maybe I should mention too, like what did Strawson figure out? So Strawson figured out that you can multiply 2x2 matrices. He found a clever way to multiply 2x2 matrices using, I think, 7 multiplies instead of 8 or something like that. And so what you do is you break down your matrix multiplication recursively into these like 2x2 multiplications, or like that's the idea anyway. In implementation, I think there's some tricks to it, but he found a clever way to multiply 2x2 matrices. Okay, so that's our discussion of linear transformations and matrices and matrix multiplication. And so like so far, matrices have been this like, I don't know, not like they depend on linear transformations to survive, or at least that's how we've presented it so far. Yeah, so poor matrix doesn't get its own character arc. Well, now we're going to give it a second reason to exist, which is systems of linear equations. All right, so now we're on to content from this week from what we discussed on Monday. And let's recall briefly, what is a linear equation? A linear equation is a linear combination of variables. So I have a few examples here. X plus y equals 1. This is a line. Down here, this is a plane. And so in general, you could have a linear combination of variables like this. And let's recall, linear combination means that we multiply each variable by some constant and then add them all up. So you're not going to see like an x squared, an x cubed in here. It's just the variables multiplied by scalars. Okay, and then a system of linear equations is when you have multiple linear equations in the same variables. So we have two equations here. We have two unknowns, x and y. And so you could solve this system of linear equations for the values of x and y. And then in general, here's like what a really big system of linear equations would look like. We have n variables, and then each variable has a constant, and then there's m rows, so there's a lot of data to keep track of. And so our goal is to take some really big system of linear equations and solve for these values here. Okay, so what can we do to this system to begin solving? Well, the first thing we can do, right, so there's these three operations we have, and by doing these three operations, you don't affect the solution to the system, which is good. But we can use these operations to get the solution. So the first thing we can do is we can scale a row by a non-zero scalar. So if I take this first row and I multiply on the left by 5 and I multiply on the right by 5, the equation like hasn't changed, or well, it has, but it hasn't changed the values of what x1 and xn can be. Like these sides are still equal. And we can't multiply by a zero scalar because if we multiply by 0, we just get 0 equals 0. So we've lost information. We've lost information about these constants here, and so we've not helped ourselves. Yeah. Okay, and then the second thing we can do is we can add a multiple of one row to another row. So I can take this row and I can just add it to the next row. So I can add all of this here onto this, and I can add b1 to b2. And because I'm adding equal quantities on the left and the right, the equation is still satisfied. And I can multiply this by 2 and this by 2 and then add, and the same thing still stands. All right, and then our third operation that we can do is we can swap the rows on our paper or on our tablet. And okay, this one seems like kind of silly. Like yeah, okay. So if I took this row and then I just like swapped it with the one beneath, if I just swap it with the row there, like, okay, obviously I have not changed my system of equations, and it seems silly, but it'll be important for when we move on to matrices. Yeah, I'm going to answer why you'd want to swap soon. All right, so these are the three operations that we can do so that we maintain our solution to the system, but we can approach that solution. All right, and now before we can talk about how we use these operations, we have to make some observations. And if you stare at a system of equations for long enough, you go, hang on, that kind of looks like a matrix. So these constants here, you could put it into a column in a matrix. And these constants here, you can put them into a column of a matrix. And then all of these additions here, that what this looks like is matrix vector multiplication. So then you look at your variables, and you stick them in a vector, and you multiply it by the matrix. And then lastly, you look at these constants on the right side and put them into a vector. So this system here is described as a matrix vector product. It's the same thing. We've just written our data a little bit differently. All right, and then you look at it for a while again, and you realize, well, the x1 always multiplies the first column, and x2 multiplies the second column, and xn always multiplies the nth column. And so like this is just kind of unnecessary data. Like we don't really need to keep this around anymore, because like obviously x1 is associated with this column all the way down to xn with the last column, and so we just get rid of that information too. And what we're left with is an augmented matrix, it's called. So we've kept all of our scalars around, and then we've combined this vector here. Right, and so we call this an augmented matrix. Right, so this contains the same amount of information as this, but now it's in a leading form. It's in a matrix. And we love matrices. All right, I'll pause here again for questions. You know, JMK, you say that. So the comment is, but what's the algorithm for swapping the rows? In fact, there is some complication to it. And we'll get to that. It might end up happening next week just because this lecture is spilling over into next week. Well, okay, no, the act of swapping a row is easy, but the rows that you swap, there's like some thought put into it. Okay, so what we're now going to do is an algorithm called row reduction. And I thought for a long time how best to present row reduction. And like matrix multiplication, row reduction is something that you just learn by doing. I really don't think it can be taught well just by me presenting it to you. It's like you have to do the exercises to really get the vibe. So I'm not going to present the entire algorithm to you with all of its numerous edge cases. We're working on vibes here today. And so what you do is you have your augmented matrix, and you look at the first row, the element in the first row in the first column. So that would be this guy here. And then what we want to do is eliminate everything below it, meaning we want all of these to become 0. So like which of our 3 things can we do to accomplish this? That's a question for the chat. Like which of our 3 things can we do to eliminate this column? That's exactly right. Yeah. So if this were like a 4, that doesn't show up well. Oh, okay. So if this were a 4 here and we had a 2 beneath it, what we would do is we would scale this entire row by 1/2 so that the leading entry is 2, and then we subtract it away from this row. So we do a scale and then a combine, as Borb said, to eliminate this entry here and to get a 0. And so you would do that for each row. And so you get zeros in each row. And that's the elimination process. And then we keep doing it. So then we look at the second row. We have a 0 here. So we look at the first non-zero entry, and then we eliminate everything beneath it again. And we continue doing this. So now we go into the third row. And what you notice about the third row is that the pivot, as we call it, is not in the third entry. It's not in the third column. We actually have to walk a little bit further to find it. And so this is like one of the complications of the algorithm, but this is the idea. You look for these pivots and you eliminate everything beneath it. What's a case where we have to swap? In my diagram here, where there's no swapping to be done. A swap would happen, let's say, if our system looks something like this, and we have a 0 here, a 0 here, and a 1 here. And then, the rest of the matrix, right? So we can't just look at the first row and the first column and then eliminate, because it's already 0. So what we do with the swap is we take this row and we bring it to the top. So we swap these 2 rows, and then we can do our elimination. All right. Yeah, so at this point, what I wanted to do is show you another professor's notes on row reduction, because I could have written it all on 20 slides myself, and we could have gone through it all, or I can just show you somebody else's notes. Somebody else's notes that are laid out quite nicely, and I think we'll do that. But we're also running low on time, and I had wanted to show you some code today, because this is what we do in the code lecture, but how do we feel about row reduction? Do we want to watch some code, or do we want to understand the algorithm better? Okay. All right. Borb gets to say, or we'll move on to some code. And I guess before we go into the code, so I don't have to keep switching back between my tablet and Studio, I want to make a remark, which is to try to relate everything that we've been looking at, because it can maybe be confusing to keep all in your head. So the first thing we did in this course, well, not the first thing, but last week we discussed linear transformations, and we showed that you can represent linear transformations as matrices. So this was our motivation for matrices. We derived their properties from linear transformations. And then today, what we saw is that you can look at it from another direction. You can look at it as starting with a system of linear equations, and then again, you arrive at matrices. And then given a matrix, we have a linear transformation. If you look at a matrix, it's not hard to find out which linear transformation it represents. And similarly, if I give you like an augmented matrix, it's not hard to find out which system of linear equations it represents. So there seems to be now like some relationship between linear transformations and systems of linear equations, and they're related by matrices. Yeah, I guess the last thing I'll say on this is that we motivated matrices using linear transformations and using systems of linear equations. But matrices actually stand on their own. You can study matrices for studying, like for the sake of studying matrices. So I don't want to give the impression that they're like dependent on these two. There's a whole field of matrix analysis out there that just studies matrices for the sake of matrices. All right. Borb says, so I'm still vastly confused on the conversion between linear transformations and matrices. Let's chat in office hours. All right. Anyway, I hope this gives you like a better view of what we've been up to. All right. So we have 7 minutes left. Maybe we can get started on something. Okay. So here we are in Studio, and I guess I should have shown you earlier the matrix multiplication. So in this matrix file, it's the same thing that we coded last week, but I've actually added a few new things in here. So I don't actually recall if we had this before, but I added a constructor to give you a matrix of all zeros. I also added a constructor to give you the identity matrix, which is the matrix of all zeros except the diagonal is ones. I added a constructor to copy a matrix. Shoot, that was going to be for homework. But it's mostly the same from what we did last week. And then matrix multiplication is here. So this is what we saw. We create an empty matrix. We loop through every entry in that matrix, and then we do a dot product. All right. So now maybe we'll just at least begin to lay the framework for row reduction. And with row reduction, we'll take in a matrix. And then let's return our function. And we're also going to need the matrix class. I apologize, I've lost the chat. Let me pull that up on my phone. Okay, so where do we begin with row reduction? Where do we begin? Because I have an algorithm set out. I have an algorithm here, but going top to bottom is not very helpful. Well, all right. here's where we begin. The first thing we're going to do is we're just going to copy our matrix. And the reason we're copying this is so at the end we're going to return this matrix, but we're going to modify it. So we want to be respectful to the caller who gave us data. We don't want to manipulate the original table. We'll just make a copy of it. All right, and then the next thing that we do is we keep track of the pivots. Because remember sorry, I think you overwrote the past table. The past table though, right? That's right. Yeah, I overwrote it just to be the copy. Yeah. So the next thing that we do is we keep track of our pivot so that we can eliminate everything below it. And so we'll do this with two variables. So we'll keep track of the row that our pivot is in, and we'll keep track of the column that our pivot is in. So throughout the algorithm, we're going to move the pivot. A lot of the time, we're going to move it diagonally down and to the right. Because you start at the first row and you eliminate down, then you go to the second row, eliminate down. But actually, sometimes we're going to keep the row the same, and we're going to go, only move the column. And so, like, what is a case where we do this? So if we had some matrix like this, okay, this is going to be a very boring matrix. Right, so here in this first row, we start at 1, 1, we eliminate down. Then we go to the second row, and we eliminate down. And then, oh goodness, that's what I meant to do. Then we go to the third row. Sorry, examples on the spot are hard. Then we go to the third row, and so we expect to find the pivot here, because we were moving diagonally, but actually the pivot's not there. We have to go to the right. So this is a case where you'd have to only increment the column, but not the pivot, but not the row. So we're going to keep doing this until one of these indices, the row index or the column index, falls out of bounds. So while the pivot row index is less than the matrix rows, and the column index is less than or equal to the columns, then we're going to do our row reduction. All right, so we're almost out of time, so I'll just give you like the high level of what we're going to do next. Is we choose a row to swap. I explained earlier, like in a scenario where you would want to swap rows because the row that you're currently looking at doesn't have a pivot, so you can't eliminate. Right, so we're going to choose a row to swap, and then we'll swap the rows, and then we eliminate rows beneath and above. And then the last thing, which I didn't explain, is that we normalize at the end, which means that we divide a row such that its pivot is just the number 1. So we normalize the pivot row. And then we increment our row and column for the pivot. All right, so not a very satisfying conclusion to this, just the skeleton of an algorithm, but we'll finish it up next week. And again, like I don't expect you to understand the row reduction on first pass. Like, this is really something that you have to do. Like, you just have to like feel it by doing it to really get it. So we'll assign some exercises for these. And if you need help, of course, you can always find us in office hours on Saturday.